Have you ever wondered how you can run Windows on a Mac? Or maybe how these giant cloud companies like Amazon and Google can serve millions of people all at once? Well, the answer to both is this incredible concept called virtualization. And in this explainer, we're going to break down exactly what it is, how it works, and why it's pretty much the backbone of all modern computing.
I know, it sounds a little bit like that movie Inception, right? A computer inside your computer, but it turns out this idea is one of the most powerful tools we have. Now, as we go, we're going to be touching on some deeper concepts, things like kernels and privileged instructions. So if you need a quick refresher, I'd really recommend checking out our videos on the operating system's kernel. They're in the OS playlist, and we'll give you some great context for this.
Okay, so before we dive into the technical nitty-gritty, let's just ask the big question. Why? Why even do this? What's the point of virtualization? It's not just a neat party trick. It actually solves some really fundamental problems in computing.
There are some huge wins here. First up, security. Think about it. If one of your virtual machines gets a virus, it's trapped in this digital sandbox. It can't get out to mess with your main computer or any other VMs. It's a massive security feature. Then there's resource optimization. Most servers in the old days were just sitting around, barely using their full power. With virtualization, you can cram a bunch of those virtual servers onto one physical box, saving tons of electricity, cooling, and money. It also gives you incredible flexibility. If you're a developer, you can have a Windows VM, a Linux VM, and a Mac OS VM all running on the same laptop for testing. And maybe the biggest one of all, it's the absolute foundation of the cloud. Every time you spin up a service on AWS or Azure, you're getting a slice of a virtualized machine.
So now that we know why it's so incredibly useful, let's start peeling back the layers to see how it all works. We need to get familiar with the key players in this whole setup. At its heart, virtualization is all about abstraction. It's about creating a software-based or virtual version of a computer that can run on a real physical computer. This virtual machine, we usually just call it a VM, gets its own virtual CPU, its own virtual memory, its own virtual hard drive, the whole shebang. And it can run a completely separate operating system and all its apps, totally oblivious to the fact that it's not a real physical machine.
To make this happen, you've really got three main characters in the story. First, you have the host. That's your actual physical computer, the laptop or server sitting on the desk. Then you have the guest. That's the virtual machine, the computer inside a computer. And the real star of the show, the magic ingredient, is the software that sits between them, the hypervisor. You can think of the hypervisor as the puppet master. It creates the VMs, manages them, and makes sure each guest gets a fair share of the host resources, all while keeping them from stepping on each other's toes. Now, as you might have guessed, not all hypervisors are built the same. There are actually two main flavors, and understanding the difference between them is really key to seeing where and why virtualization gets used.
So you have Type 1 and Type 2. A Type 1 hypervisor is what we call bare metal. It runs directly on the server's hardware. It basically is the operating system. This is the heavy-duty stuff you find in cloud data centers because it's super efficient and gives you the best performance. Then you have a Type 2 hypervisor. This is probably what you've used before. It's a regular application that you install on your existing OS, like Windows or Mac OS. Think VirtualBox or VMware Fusion. It's fantastic for development or just trying out a new OS on your desktop. But because it has to go through your main operating system to talk to the hardware, it's just a little bit slower.
All right, we've covered the what and the why. Now it's time for my favorite part, the how. How in the world does a hypervisor trick a full-blown operating system, something like Windows or Linux, into believing it's running on its own dedicated hardware? This is where things get really clever.
One of the classic techniques is called trap and emulate. Here's the play-by-play. The guest OS is just running along, and then it tries to do something sensitive, something that requires direct access to the hardware, a privileged instruction. The physical CPU is designed to spot this. It immediately throws up a red flag and triggers a trap. This instantly pauses the guest and hands control over to the hypervisor. The hypervisor then looks at what the guest was trying to do, and it emulates that action for it, but in a safe, controlled way. The guest gets what it needs, and the host machine stays safe.
Okay, so trap and emulate sounds like a perfect solution, right? Well, there was a catch. Early hardware, especially the original x86 chips that powered most PCs, had some sensitive instructions that the CPU just couldn't trap. The instruction would just run, potentially causing chaos. This was a huge roadblock for the pioneers of virtualization, and they had to come up with an even cleverer solution.
And that solution was called binary translation. This is brilliant. Instead of waiting for the guest to run a dangerous command and hoping the CPU catches it, the hypervisor gets proactive. It scans the guest's code before it ever runs, finds those tricky, non-trappable instructions, and just replaces them on the fly with a new set of instructions that are perfectly safe. It's like having a real-time interpreter that's constantly sanitizing the code to make sure nothing bad can happen.
So virtualization has obviously come a very long way since those early days of trap and emulate and binary translation. And today, the evolution of this core idea has led to a whole new approach that's taking over the software world, something lighter, faster, and way more efficient.
And that brings us to the big discussion in modern tech: VMs versus containers. A VM, as we've said, is the whole package. It emulates a full computer, and it runs its very own guest operating system. It's big and it's heavily isolated. A container, on the other hand, is much more lightweight. It doesn't need a full guest OS because it shares the kernel of the host operating system. So you get this classic trade-off. VMs give you maximum isolation and security, but they're heavy, we're talking gigabytes, and can take minutes to start up. Containers are tiny, megabytes, and start in seconds, but you lose that super strong isolation.
So think about this. The first big wave, virtualization, was about abstracting away physical hardware. That move literally gave us the cloud. Now we have containers abstracting away the operating system. So it leaves us with this really exciting question: what's the next layer of abstraction going to be? What kind of incredible new technology will that enable? I'd love to hear your thoughts on that down in the comments.
And that's a wrap on our dive into virtualization. Hopefully, this cleared some things up for you. If you found this explainer helpful, do us a huge favor and hit that like button and make sure you're following for more deep dives just like this one. Thanks so much for watching, and we'll catch you in the next one.